So now in the process of generating a measurable signal that we can deal with in the camera or the computer, we have to get that visible light measured. And the question here is, how do we convert a scintillation light to an electrical signal? The process that's being used is that of a photomultiplier tube. It's a bit different from what we use with our CCD cameras in our cell phones. So we have the scintillation crystal. Here is the example of sodium iodide. That's the whole process. We have the photomultiplier tube here, which the signal that it produces is being amplified. There's a pulsate analyzer, PHA stands for that, and that displays the signal. Now, what I'm going to discuss now is what is inside this photomultiplier tube, what is the process that is going on. So first we have the photocathode, we have the photomultiplier tube in vacuum, and there are subsequent anodes and cathodes. These pairs of anodes and cathodes here, we call them dynode. And we have the final anode here, which is where the signal is finally being detected. One applies a voltage, and this is a typical example. This goes from in increments of 150 volts, 0, 300, 450, 600, 750, 900, etc. until 1.2 kilovolts is the voltage that's being applied. And at the end, a signal is being detected that is sent to the pulsate analyzer. So let's say we have a visible photon that impacts the photocathode. What it does in the photocathode, we won't go into the details here. It liberates one or more electrons. Let's say it liberates one electron. This electron from the cathode is accelerated towards the first anode, where it liberates again more electrons. We'll take here the example of 2. So 2 electrons, out of 1 we make 2. At the next point here where it's accelerated towards, we have, again, we'll keep the factor, we'll always assume that's a factor of 2. 1 electron produces 2 electrons, so now we have 4 electrons that arrive here. We produce, again with a dynode, we go from 4 to 8 and then to 16, and finally to 64 electrons that go to the pulsate analyzer. So this process essentially allows us from more or less a single photon here, allows us to produce a measurable signal of many photons, of many electrons, that we can measure the change in signal, the electrical signal of those electrons when they arrive to the final anode of the photomultiplier tube. And this is actually technology from more than a half century ago. It is providing virtual noiseless amplification of the signal. Now, what does a photomultiplier tube look like? Here it is. We have here the photocathode, we have the subsequent dynodes, and here are the connectors that connect to the instrument. Let's think of what the dimensions of this is, and to give you a scale here, this is roughly a centimeter. So these are they're almost like the size of a salt shaker, right? So, but wait, let's think. We want to have images with a spatial resolution typically on the order of millimeters, but we have, in the end, the units that detect our signal, they have dimensions on the order of an inch, 2 centimeters, so salt shaker size. So they are bulky, they're not adapted to the resolution that we would like. To give you an idea what this looks like, here we have such a detector board. Here's the scintillation crystal, here's the waveguide, and here are all these photomultiplier tubes. Looks like a happy family of salt shakers, doesn't it? Yes, but now, how do we get high resolution images from this? How can we increase the spatial resolution beyond the physical dimensions of the photomultiplier tube? That's the question. How do we improve the spatial resolution of the photomultiplier tube? Let's consider the situation here. We have a sodium iodide crystal of 40 centimeters by 40 centimeters size. It's perpendicular to the plane. We have a light guide, and then we've drawn 3 photomultiplier tubes. And we'll say that their position of these 3 photomultiplier tubes is x1, x2, and x3. We have a X-ray that interacts with the scintillation crystal, so it produces scintillation light. This scintillation light is detected, in this case, by all 3 photomultipliers, so they multiply the signal according to the number of scintillation photons that they detect, and therefore we obtain now from this single photon here, X-ray that has impacted here, that has made the interaction here, we're obtaining in these three photomultipliers three signals. We'll call this intensity 1, intensity 2, and intensity 3. So what we have said is the number of scintillation photons produced is proportional to the energy of the X-ray. So we have energy information. Now how do we get the position of the X-ray figured out here? Well, just from the intensity I1, I2, and I3, if I measure it this way, I can say, well, it's not centered on I2, because this is higher than I1, so somewhere the event must have happened, with these intensities, must have happened here along where we have the dashed line. The precise calculation is done with this equation here. We'll multiply the intensity of each of the photomultiplier tubes with their position, and we'll divide it by the total intensity measured. That gives us the precise location of the photomultiplier tube. This is just done for the dimension of x. We don't need to worry about how we do it in 2 dimensions. Once you flash back to where this equation comes from, where we've dealt it, it becomes fairly apparent. Does this equation look in any way familiar? Well, think back. If you've had a physics class, you most likely have had the concept of center of mass, and the center of mass in mechanics, in a mechanics physics lecture, had this expression here. So mathematically what we're looking at here is a center of mass calculation where we replace the mass by the intensity of the X-ray. So we have this equation here that gives us the position of the X-ray in the scintillation crystal, and we can measure clearly with different intensities in the photomultiplier tubes this position with a precision that's higher than the physical dimensions of photomultiplier tubes. This is technology that was developed in the 1960s. It's actually named the Anger Positional Network. It's named after Gentleman Anger and has nothing to do with the term anger as such. So it's Nomen est Omen here.